Now, obviously, that is just a funny video, but the movement of the tectonic plates, we have pretty good evidence that is actually happening. And so, when we watched the video talking about the Earth and its development, what seemed to be an answer for a lot of things is this: time. And so, if by chance the Earth is very old, and we now believe it to be over 4.5 billion years old, here is how we can explain the geological processes that we see today. What can happen is that if you have very slow changes over time, then all the processes that happen can account for the way that the rocks look, how the crust looks, how fossils are found, and this was offered by James Hutton in his idea. Charles Lionel is credited with furthering this idea and produced the term, which is really a misnomer, principle of uniform change, to describe how the Earth has changed. But really, in geological processes, we know that sometimes it's active and sometimes it's very passive. Sometimes lots of things are happening. And so we, over long periods of time, can only see what has happened by the average, but it's do a whole lot of stuff and then stop, and then do a whole lot of stuff and stop, and do a whole lot of stuff and stop. But it looks like there's constant change. Now, if we can bury a little bit of dirt and then bury a little bit of dirt on top of that and bury a little dirt on top of that, and it gets all compressed and you get these layers of rock, just small little changes over long periods of time, Charles Darwin took that particular idea and applied it into biological systems, such that if you get a little bit of change and then a little biological change and a little biological change, you can have very large changes, and he described it in the theory of evolution. So gradual changes in biology lead to larger changes. Now, when Charles Darwin actually described his theory, he indicated that it needed evidence for it to be accepted. And the evidence that he wanted to see and what he was trying to find in the fossil record was what he calls transitional forms. And so it is the forms between one species and the next. Now, right now, I don't care if you are a Christian or not Christian, there is evolutionary processes occurring all the time. And you can look at it by looking at the simple fact that, there are some strange named dogs breeds that you can get. Okay, I don't know. I think this is a snickerdoodle, but no, there's all kinds of poodle mixes and things of that nature that actually look different. Their sizes are different, the way that their hair is different, and we have bred different dogs from apparently two dogs that had different structures. We have also done that with plants, and we do manipulation by breeding plants to get new forms. And so that actually occurs, and a lot of people who are scared of the term evolution because it brings connotations of a godless event, most people will agree that the term microevolution or adaptation occurs, and almost nobody has a problem with that because we actually see it even over our lifetimes. Okay? They just won't call it evolution because that has a meaning when you use that terminology. What distinguishes adaptation and evolution for most people is this, that a dinosaur drops an egg and you have an egg there and then all of a sudden pops out a bird, changing from one species to the next. That is where the theory of evolution has a very large problem in terms of showing any evidence in the fossil record that it has actually happened. Even in the most optimistic look, there have been a handful of fossils that people have attempted to identify as a transitional species, but there are just a handful, 5 or 6 that are being debated. And if you look at all of the fossils that are found and everything, there should be a lot more there to support the idea that the evolutionary process might have occurred in the way that Darwin described it. In actuality, even atheistic evolutionists do not hold true to Darwin's theories. They've made changes to that. Unfortunately, high school textbooks have not kept up, and they teach the Darwinian view very often without context. Now, reading the rock, okay? History can be looked at if we dig down in rock. This is the principle in which we interpret what is under the earth. And so different rock is formed under different conditions. And so that if you dig down and there's a different kind of rock, then at some point in time at that place, the type of climate and type of what you see in terms of what's in the year and what kind of foliage and things of that nature was different at different time periods where those rocks were being formed. And so if you dig down and you have gypsum or salt, you find that it most likely may have been a desert. If it was coal, we have evidence that swamps were at that place at some point in time in the past. And if you find limestone with fossils, it most likely was a shallow sea in the past. And so you can dig down and you can find all sorts of different areas or different types of rock, even in the same area. So that area itself in the history has changed its climate in lots of different ways. And so here is an example if we actually dig down really, really far, okay? When we look at it, sedimental layers, the deepest is the oldest, okay? And we know that sedimentary rock lays down flat or horizontally, so it had to lay down flat first and then put pressure on it to bend it. And those come with tectonic plate movements, okay? And igneous rock, like the granite, okay, is liquid rock that actually, if it goes through a layer, it has to be younger than that layer. And so it comes from the center of the earth, and if it goes through a layer that had been laid down, it'll melt through, and so that is the youngest. And so if we take a look at this particular picture, okay, which layer is the youngest? There are 2 possible answers. Which layer might be the youngest here? Which one? D? Okay. D could be possible. Okay. But D had to be laid down. D was deformed. And look right here. What's on top of D? E. E has to be younger than D. Okay. So E was laid down and some erosion happened. And so E is one of the possible youngest layers here. What is the other possibility of being the youngest rock? Not C. The granite could be. All right? We don't know. We know that the granite is younger than D, right? Because it goes through D. But do you see E and D and C all have been eroded away? So has the granite. We don't know if the granite actually got all the way through E and was eroded down, okay, because E was going to be on top of D, and so granite could be the youngest. I don't know. E could be the youngest. So at this point in time, we have two possibilities we don't know. All right, there's a fault. That's a break in the crust. Did granite come before the fault was formed or after the fault was formed? Before or after? Before the fault was formed. Okay. You say after. Okay. So let's think about this. You have to have pressure, and the layers were pushed so hard that they broke. Okay. And the line of breakage went through D and C and B and A, even the deepest layer. But look, the break stops right there. If the fault was created and the granite was there before, then the breakage should be, and we should have a line all the way through. So it must have broke, and then the granite invaded, because the granite is not broken in the same way. It wasn't shifted. And if it was embedded before it got shifted, it would have broken. And so the granite came after the fault break. All right, this is the kind of rationale that we're going to use to look at layers of rock. So unconformity, it's where layers were laid down, and then all of a sudden something spectacular happens, and all the layers are at a different angle than the most recent layers. And so you can see that in the bottom layer of this picture, okay, all of these had to have been laid down flat. They couldn't have been laid down on their side. So they were flat at one time. They got pushed over on their side, and things started wearing away. And after time, we started building new layers that were at a different angle. And so the edge between layers that are over at one side and then layers that would be laid down flat is an unconformity. And picture along the side of a road, you can see that all these layers at one time were flat, but now on their side, if sediment builds up upon them, it's going to build in a different direction than what they are. Now, the layers of the rock, we assume that the deeper we go, the older it is. And that actually works out almost all the time. There's really no example of it not working out that way. But what we do is we have the ability for some rocks to do radiometric dating. And so remember way back when with half-lives, if a rock is radioactive, then if we know how much of the original is there and how much of the daughter is there, so the parent and the daughter, we can compare those two, and we can know how many times it has decayed in half. And if we know the rate, which we know the rate of all the radioactive material out there, then we can calculate how many half-lives went and multiply how many times the half-life is times the length of time for a half-life, and we can date things to a particular time period. Now, the kinds of radioactive material, these are all kind of unknown to you, except for, we talked a lot about uranium, okay, being something that has a half-life. But look at the time periods. The half-life of one of the versions of uranium is 4.5 billion years. The half-life of these radioisotopes are in the span of the lifetime of the Earth. And so what we can do is we can measure a very good concentration of one of the items, uranium, and be able to measure the amount of the lead very carefully. And by having both of those measurements, then I can do a very good calculation. And so to get the ages that we're seeing, we have to find the radioisotopes that have half-lives that are long enough for us to do the calculations. So potassium to argon, rubidium to strontium, thorium to lead, and the uraniums are the ones that we look for. Here's the problem. Not every layer of rock has radioactive material. Only a few of them do. And so we can't date everything that you dig up. If you bring me a rock, most likely I'm not going to be able to date that sample. I can't send it off, can't pay money to get a date. I can throw something out, tell you how old it is, but it's very hard to find ones that do. Although we do find rocks that are radioactive, and we can date them. All right. Now, young Earth perspective versus an old Earth perspective. How do you argue against radiometric dating? Okay. Here are a couple ways, and people have made these arguments. All right. If you believe it to be old, then everything you do, all of the measurements that you take, will result in something that is old. So what they're saying is their bias in how the scientists manipulate the data, so it always comes out to be old. Okay? That has an underlying issue of, well, then you have to distrust everybody, and you have to make an argument that, well, if you're not Christian, then you're just not ethical. Okay? And that's a little harder to believe. Okay? Here's one in which there's no ethics involved. All right, the radioactive half-lives. If we measure it now, we know its rate. Okay? There is the argument that this has happened, that the radioactive half-lives are not constant. Just like if I see a car going down the road at 20 miles an hour, okay, then that car always goes at 20 miles an hour. Okay? And so, but what they're saying is, well, the car is only going 20 miles an hour because it's a school zone and there's a cop right there. If the cop wasn't there, the car might go faster or slower. And so the radioactive half-lives, the constant value, has changed over time. And so when you do the calculations, it might calculate old, but it's because you're assuming something's constant and it's not. That's a more valid argument in terms of how an old measurement might come out wrong in terms of doing things. A counter to that, there are samples in which there are different isotopes. Okay? The isotopes have different half-lives, so they're moving at different ways. The two isotopes, when taken, come to the same date. What you would have to assume is that one isotope is not constant in its rate, right? And the other one is not constant in its rate, but they have to be perfectly balanced that both of them are not constant in the rate and change, but actually end up at the same place, which is a much harder thing to believe when we have samples that have multiple ways to measure its age. And so that one's a little bit harder to believe. And then there is the idea from some young Earth perspective is that when God created the Earth in those 6 days, he made the Earth look old. He created it aged. And so if you date it old, that's how God wanted it to be, and that's how he created it. So that's another way around having a very young Earth that might look old. All of those, some people believe and some people hold to, each one of those types of justifications. Carbon-14 dating, probably the most controversial in terms of the dating methods, because there's way too many assumptions. Carbon-14 is created in the atmosphere by the use of the UV radiation and the material that comes off the sun. And so the carbon-14 is always being created by the sun. And the CO2 is incorporated into plants, The animals eat the plants, we eat the plants and the animals, and so we're distributing carbon-14 throughout all biological samples that are alive. And we assume that everything has the same amount of carbon-14 in it. All right? The other problem is carbon-14 decays into nitrogen, which is a gas. And so a lot of times that gas leaves the sample. So all we can measure is the parent. We can't get a good measurement of the daughter. So we only take one half of the measurement, not both of the measurements. All right? Because it has a fairly short half-life, we can effectively date something 1,000 to 40,000 years. And what we measure is how much carbon-14 is left. We assumed how much was there at the beginning, and we make our calculations about how many half-lives were there. In this method, the assumption that carbon-14 is constant throughout all the time period, that's a leap of faith. And then your measurement, it is such a small amount of the material that is there, making measurements that are very, very accurate. Little tiny changes can change the date a lot. And so there are a lot of assumptions when you do carbon-14 dating. If you send off a sample to a lab or to several labs, you actually may get several different values, and they can be very significantly different. And so carbon-14 dating is a little sketchy. The theory is perfectly fine, but you have too many assumptions. If you can measure a good amount of the daughter and you can make a good amount of the parent and you can make sure that all the mass is there, more confidence can be made. And so some of the other dating methods are much more valuable in terms of reproducibility. All right. So we can look for rock that is older, and sometimes we can actually really measure it by radioactivity. Why we're really looking in the layers is what we're trying to do is find evidence of what happened in the past. And we're really looking at what happened in the biological realm. What kind of plants were there? What kind of animals were there? What is happening in history? And so what we're looking for in those layers of rock, not just that we find rock, but that we find things in them. The only layer of rock that fossils are found are in sedimentary rock, because the fossil, things have to fall into the material, and then it has to be buried, and that's a rock that is made up of sedimentary. If something falls in igneous and lava, it's going to burn up. If it is sedimentary and it gets metamorphosized, then it gets cooked and moved and changed, and so you lose the fossil. So I'm looking at layers of sedimentary rock. The things that become fossils are hard parts of animals, and so they get buried. But what you don't have is the tooth of a dinosaur or the bone of a dinosaur. What actually happens is it gets buried, and the bone and the teeth are made up of minerals. Okay? What happens over time is the original mineral, which is usually relatively soft, gets exchanged for rock minerals. And so a fossil is a rock that has replaced all the minerals of the bone originally, and it's in the same shape as what it was originally. It's now rock. And so we're looking at the shape of what was buried. Okay? And so the harder parts of animals are the most likely things to fossilize. All right? Rarely do we ever get a whole specimen, and so we have found frozen woolly mammoths complete, including the plants that were in their mouth and in their digestive tracts that were still there when they were frozen. Like Jurassic Park, the idea of insects that get trapped in tree resin, the sap, and then that hardens, creating amber. That is actually, we do find those. But they are very, very rare. Even more rare is material that is a plant. We find them under special conditions. Okay, let's think about this. A tree lets a leaf fall to the ground, right? Is that going to become a fossil? What usually happens to a leaf when it falls off? Yeah, it dries up, it crumbles, and it becomes dust. Most things that are soft and plant-like do that. They dry up and they break apart. For a fossil to form, it really needs to fall into something that is soft and that is away from the atmosphere. Most fossils were formed in really shallow seas, okay, or riverbeds where it falls down into the muck and mire and gets trapped and fossilizes out. This is not something that happens very often. And so to get a fossilization of a plant, it's really hard to do. The exception is this. If the swamp gets buried completely, it turns into coal. Parts of that don't get transformed have plant material, and that's where we get a lot of our plant fossilization. Petrified wood is a rock that looks like the trunk of a tree because the trunk of the tree got buried in the bottom of a river and got converted into stone. It looks like a tree. And if you ever took an axe to it, you would be really hurting because it is a rock. And so petrified wood is quite common, but things like the leaves and structures of plants are much less common. And then even more rare is trails or footprints that are trapped in sediment. So you walk through mud, it has to be buried very quickly before it is eroded away, and then you can have examples of that, and there are some examples of tracks that have been discovered. But you have to bury it quickly, okay? One interesting thing about fossils is that a lot of the animals that are fossilized seem to be running away from things, okay? It has to be trapped under sediment, under the ocean. A very logical way to capture lots of fossils is if there's a big rush of water and it buries everything and kills everything. In terms of justification from the idea of a young Earth's perspective, and the flood does a lot of things, the flood makes a whole lot of sense about why we may have animals trapped under in layers. And so that makes a really kind of intellectual, that tests, that passed the test of time. Also, a lot of fossils are of sea creatures. Now, that could happen because the flood happened, but conversely, most scientists think that a fossilization happens in shallow seas, so we have a lot more examples of fossils from things that lived in the ocean than things that lived on land. So both ways are justified in looking at that particular piece of the puzzle. Okay, in general, fossils that are in deep, deep layers that are very, very old have structures that are relatively simple, much less complex. And as you get higher and higher or closer to this age, it seems like the plants and the animals become more complex. That seems to be a really stable thing that is seen all over the world. Okay, here's an argument. I think it's weak, but here's an argument. All right, the flood is coming, and you have simple animals, you have complex animals. The complex animals might be able to make better decisions or swim better, and so they get trapped in the higher level layers, and those that are simple might not be able to swim as good or can't react as fast, and so they tend to end up in the lower levels. And so in that, you could have distribution of different kinds of complexities in different layers. Okay, that one doesn't sound so bad. This is where it gets me. You've got to use that same logic for plants. Hello? Is the simple plants not able to swim as good as the complex plants, so that the complex plants end up at the top and the simple plants end up at the bottom? That one's where that particular idea, for me, falls apart. There is no justification of why simple plants should be lower and more complex plants be higher. But maybe with the idea about the animals, that might ring true. And so if it is very deep in time and complexity within the biological system develops slowly, things that were formed way back when are simple, and more complex are closer to this age, that makes some sense in terms of why you might find it that way. All right, old versus new. Here's a lot of times what happens. You might find a very particular fossil. It has a certain shape. It's a certain animal. And it also happens to be in a layer that's radioactive. So you can date it. And you get a good date, which is called an absolute date. I know absolutely what date that was buried and the fossil was made. If you find that particular animal in that particular shape anywhere else on Earth, what scientists normally do is they date that fossil relatively. It looked like that when we have a date, so this one must be dated this date. And so in that, scientists are pretty okay with making that assumption, but that leads to the idea that maybe it was buried, but maybe not at that time. And so absolute dating can be justified. This relative type of dating could lead to ideas that, hey, you're just making it up just because it looks that way. An example of something that might throw this off, sharks in an evolutionary model are very, very old. The shapes of sharks and how they behave and their biology hasn't changed for long periods of time. And so one that was buried in one layer, a modern day shark buried in a certain layer might look older, or we might relatively date it older by what we see. Also, there have been things that were extinct for long periods of time, and we thought it was extinct for millions of years, and then all of a sudden you find that particular animal living. And so every so often there are examples like that, which then kind of throws things off in terms of absolute versus relative dating. And so even though the scientific community really kind of believes in this, and there's some support for the idea, it does open the possibility that because you believe what you think is true, then you make it fit the way it is true. And so there is an area in which there can be uncertainty because of that. Okay, here's the real data about the fossil record. It is much, much less complete than you think. Okay, textbooks show lots of things that move, and they've got lots of examples, and museums have lots of fossils and displays, but the problem is only one of those displays is real. Many of the displays that are in museums are copies of the one that was found and shared all around the world. And so we do have fossils, and they do make sense in order of time of what we see, but it isn't an overwhelming number of fossils. There's a good number, but it isn't as complete as maybe you might get a sense when you read things. And so there are big gaps, and there are things that are missing. The worst offender is the samples of biological fossils that are hominids or man-like creatures. And so there are somewhere about 14 examples that create that picture of the ape to man, that very famous picture. And of those 14 skeletons, none of them are complete. Some of them may have 7 or 8 bones of the 206 that are in a human body. Some of them have 1 bone, and they extrapolate a lot of data from those small samples. And so we have wonderful pictures in books, but much of that is drawn by artists that have a perspective that it is happening this way, and so their art goes that way and interpretations go that way. And so for it to be much more valid, I would expect that you would have a lot more samples, and we just don't.